Good afternoon, this is Schweitzer, and we're going to run to our first introductory video into equilibrium. What is equilibrium? How does it work? What should we expect from equilibrium? Well, equilibrium is really a process that happens everywhere in our society. Anytime you have one or more processes competing against each other, then you have an opportunity for an equilibrium type situation. You could even, sometimes I make the analogy, let's say, of laundry. You know, you have, in my house, I do all of my own laundry, but all my laundry either starts at one spot and then it's all done the same day. And at one point I have all my laundry is essentially clean. Where some families are bigger, and this is the process of making laundry clean, and this is the process maybe of making it dirty. So if you have a big family, you might realize that all your laundry is never clean. It's just constantly, and maybe that wash machine's kind of always going. So there are processes in nature that are one way, and there are processes that are constantly competing back and forth. Another example that I might make would be in a person's human body. It is all about equilibrium. Everything is. From standing up to breathing to everything you do is a balance. Let's say, for example, blood sugar. Okay, if you're diabetic, you really understand the equilibrium of your blood sugar. Sugar is entering your cells, okay, and there's a basic chemistry between the two things. What enters your body and your blood sugar is really important. It cannot go too high, it cannot go too low, and you need to balance that in a certain range. Other people who aren't diabetic don't really realize it. In your body, the amount of carbon dioxide in your body will also be regulated to the point that your lungs expel CO2, and your metabolic processes are producing carbon, and therefore you must release it as carbon dioxide. If you can't release it enough in your lungs, then your body will literally pee it out in the form of carbonate. So it's all about balance and between two processes. Your body temperature is a really important balancing process. Too hot, not too cold. Your body will go through all sorts of changes to release heat or to generate it. Alright, so in chemistry though, we're going to have a couple different processes. One is going to be what we call just solubility. Again, this is two competing processes. If we have a saturated situation here, we have stuff dissolving, and we have stuff sort of precipitating. It looks like nothing is happening, but if you add more water, more stuff will dissolve. So this is just a basic introduction into just the types of things you're going to see. So solubility is one of our main things that we're going to be looking at as far as equilibrium is concerned. Vapor pressure. This is one that's in and around our topic, but we don't look at it as closely mathematically, but it is there. We have stuff evaporating. If we're in an enclosed container, it should be apparent to you that a jar of pickles in your refrigerator doesn't just keep evaporating more and more water vapor or pickle smell. As soon as you open it, seconds later you smell it. It's there. But eventually these particles start working their way back into solution, and we get this balance. We call this pressure here vapor pressure. VP. And we talked about that last chapter as far as when this thing will boil. Alright, just general chemical reactions. So, some chemical substance will produce or convert to something else, and back and forth. And they just compete back and forth, back and forth, back and forth. So, equilibrium is pretty common in everyday life and in chemistry. So, in this section, we're looking closer at that. It's kind of like stoichiometry. It is a lot like stoichiometry. Chemical reactions can either run to what we call completion, or they can run to equilibrium. When a reaction runs to completion, it runs until something runs out. This is all of stoichiometry, which we are pretty adept at and should be getting better at. So if a chemical reaction runs, let's say CH4, and we're burning an oxygen, then this is going to run until the organic substance runs out. If you're having a campfire, the fire burns until all the logs are gone. So in this case, I'm going to lose, let's say, if I have 10 of these, I would, lose, and I have excess of these guys, 0 and 0, I would lose 10, lose 20, gain 10, gain 20, 0, and then I don't know how many I have left. And really the concentration of the atmosphere doesn't change by a little campfire going. This is methane, by the way, which would just be the simplest organic compound, really, that we can have. So, with that being said, we are always trying to model and or look at these things. This one says we have 32 grams of methane burns. Methane would be, in this case, I use 10 here, but 32 grams. Grams to moles. 1 mole weighs 16 grams for carbon. That's 12 and 4. So 32, that's just, what, 2 moles? Okay. So I'm not too concerned with the amount. You could put 2 in there if you want, and then you have the same ratios. Either way, let's say that this thing runs, that the carbon runs out right here. So the organic compound oxidizes fully and is removed at that point there. What would these guys look like? Well, first of all, this particular chart might need a little more room here because I've always been meaning to move this thing. Well, can't do that. So what we have here is rates produced. Okay, now in the carbon dioxide, for example. Alright, this stuff is being consumed the same rate this stuff is being produced, 1 to 1. So my line for the carbon dioxide really needs to look metering that guy, which is why I need more room here. And then the water here is being produced at twice the rate. This should be 20. So this guy is going to look like this. If this is a distance, this should be the same distance. Now, in this case, note that everything stops at the same time, because you can't be producing carbon dioxide and water without consuming the methane in this case. And then the reaction just stops. So it literally stops. And this is a limiting reaction. The reaction stops. Reaction stops. This is different than, let's say, an equilibrium situation. Equilibrium never stops. And that's kind of an important thing just to pound into your brain. This thing doesn't, the evaporation doesn't stop. It may come to a situation with a forward reaction, and we call this the forward reaction. And the reverse reaction dropping in is called the reverse reaction. This, if the net balance is 0, it looks like it stopped. Equilibrium always seems like it looks, okay, like it stopped. But it really didn't. Okay? Never stops. You take the jar off, escapes. Now the forward reaction picks up. Alright? Again, producing more. It's still going. You don't have to shake it or do anything to get this thing evaporating again. Take the jar off, and then put it back, some escapes, and then you just happen to experience a little bit more of that forward reaction. Okay. Here's the answer key. This has got the actual numbers on here, okay, just so you know. There's my chart. This is a little distorted here. Notice we want this to be a little higher. Alright, so here's our question here. This is going to completion, stoichiometry-wise. Take a moment, give it a try. Pause the video. Alright, a mixture of carbon monoxide and oxygen are placed in a container as shown above. which the best represents the box after the reaction has proceeded and as completely as possible. So going to completion, that's important. So this might be nice just to do a little ice table. CO2 plus O2 yields CO2. And at this point, one of those and it should be CO. So it takes two of these and one of these to produce two of these. Each one grabs an oxygen. I got 1, 2, 3, 4. 4 of these, initial stoichiometric ratio end. I got 1, 2, 3 of these. So it's going to be, this is going to run, this guy will take an oxygen to that guy, this guy will take an oxygen to that guy, and then this guy will take an oxygen to that guy, and this guy goes on to that guy. So I have one left. Okay, so you could do it that way too. I think the ice table works better, cleaner, and in the middle of a test, it's maybe easier not to make a mistake. Minus 4 to 0. For every 2 of these, I only need 1 of those. Minus 2 to 1. And I'm going to get 4. 2, 1, 2, 4, 2, 4. This is what my picture should look like in the end. Which one has no carbon monoxide? That would be this guy right here. So all of them are showing no carbon monoxide. Okay? Which is nice. Okay? I don't see any of those. Which one has 1 excess oxygen? This guy's out. This guy's got several excess oxygens. They're out. 1. This guy's got no excess oxygen. This is my answer. And I got 4 of the other guys. Alright. Completion, reaction runs out. But if we have an equilibrium situation, X going to Y plus Z, the reaction starts out with only X and is product favored. Complete this graph to the left. Okay, so we're going to complete the graph here, label the lines X, Y, Z. So again, let's label this out. We got our forward reaction is the one that goes literally from the left to the right. What you list on the left side of the paper is to the right side of the paper is the forward reaction. Reverse would be what you have from the right side going back to the left side. What does product favored mean? It means in the end, if you have a teeter-totter here and you're balancing, if your products balance your reactants, meaning you have the same amounts, you should say, then at that point, then we'd be right in the middle. But if you have more reactant and these are all at equilibrium. Now again, what does equilibrium mean? It looks like, well, the forward reaction rate is equaling your reverse rate. Okay? So, again, sometimes I make an analogy maybe like a basketball game where one team A jumps out to a big lead and maybe they have a 10-point lead and then team B has nothing. And then at some point, they just at that point stay that way. Basketball's kind of common that way. All of a sudden it's 30-20. Then it's 40-30. We've maintained the same 10-point spread. Looks like nothing's changing. The score is changing, but really we're in balance. And that's kind of what happens here. The reaction's still running, but the forward rate is equaling the reverse rate. So we're getting no net change. It looks like nothing's happening. Okay? Looks like things happening. So this, if you have more reactant when you're at your balance point, I often call equilibrium, I think a better term for it is stalemate. Okay? In a stalemate, you don't stop. You're just kind of stuck, between two processes. If you have, so if there's less reactant at stalemate, then we're product favored. If there's more reactant at stalemate, then it's reactant favored. Okay. So now they're telling us here this thing is product favored. So I want to make sure I draw a graph or a line or representation where I have more product in the end than I do reactants. So The reaction starts with only X. So we're going to put X up like right here. And then what my Y and Z are going to go here. Keep in mind the Y is produced twice as fast as the X. And I'm going to take and possibly move my X down a little bit, just so I can maintain my proportions a little better. There we go. Alright, so let's try it out. And I just could even decide I'm going to run at equilibrium right here. So equilibrium is going to run right here. So that's when the stalemate is going to occur. So I'm going to just draw a line down. It's going to say right here, and it flattens out. The Y should be being produced at the same amount. Okay, so I might run up with something in I could have probably done this a little bit different. Let's do a little bit more so I can cross out. Okay. Let's do a little bit more aggressive on the X, just so that I can. Okay, like that. Notice I don't go to 0. You cannot go to 0. Y would be produced something like this. And the Z would be twice that, like that. That would be a nice representation. Is there more than one option? Absolutely. And they don't got to be perfect. A couple things we might have on a test here. Make sure they all end at the equilibrium. They don't change after that point. And your rates, make sure that the Y is and the Z are 2 to 1. You know, that the Z is being produced, or at least more. Okay? That would be a point on a quiz or test. Alright, so how do we track equilibrium? Okay. Well, in equilibrium, we use a K to track equilibrium. K is a ratio of the concentrations of products and concentration of reactants. Okay. So this is just a quick introduction that we're going to use these concentrations to track where we are at the end. We mentioned that if we're at the end like this, then we are reactant favored because we have more reactant in the end than we do product. If we end up the other way around, okay, so is this reaction product favored, reactant favored? Will it be reactant favored? Okay. What would it look like if we're product favored? Well, then we would have to have more product in the end than reactant, like that. The K value is simply a way to track this numerically. Okay. So we're going to track concentrations on a graph. Or could we be represented something like this? So just our next video, we'll talk a whole bunch about K and how it works and how we set it up. But essentially, we're tracking concentrations. So a little heads up here is that when we track concentrations, then we really can only track things that have concentrations. Okay. So what things have concentrations? Well, aqueous things have concentrations, and gases have concentrations. Like you could have in this case, a number of particles per liter of space. That's the molarity, which we typically use. Aqueous things can do the number of moles per space of the solvent. This is a concentration. What things don't have concentrations? Everything else. Solids are pure, same throughout. Concentration doesn't change. Liquids, pure throughout. Things don't change. These don't have concentrations, and you'll see that in nature, these things don't affect equilibrium either. Let's stop there for a moment, and let's pick up more about K and how K works in the next video. Thank you.